We can start. Welcome everybody. So this is the Kavli Asian Winter School on Strings, Particles and Cosmology. This is the 16th in the series of Asian Winter Schools. And it would have been really nice to have all of you in person here in Bangalore. So this is usually organized on a rotating basis between China, Japan, Korea, and India. And this winter school targets young researchers, primarily in their a bit advanced stages, graduate students, postdoctoral fellows, and active researchers in the field. So this year we have all the lectures on Zoom, and we are very thankful for ICTS for coordinating this. So the first lecture is going to be on machine learning by Professor Yang-Hui. So you can read about Yang-Hui on his Wikipedia entry. He's a mathematical physicist who's a fellow at the London Institute, a Royal Institution, professor of mathematics at City University of London, a Changjian chair professor at Nankai University, as well as a tutor and former fellow at Merton College in Oxford. So he works on the interface between quantum field theory, string theory, algebraic geometry, and number theory. And more recently, over the last few years, he has been interested in how AI and machine learning help with these problems. So we are sure to have a very exciting lecture. So since there are a lot of participants, I would like to suggest that Yang takes questions every 20 minutes or so. And if there are any questions in the chat box, which I will deem as relevant, I will read them out when the time comes. So please feel free to drop your questions on the chat box. And if there are other pressing questions, there is also the Slack channel, which you should make use of. So over to you, Yang.
Thank you very much, Aninda, for the kind introduction, and thank you very much for inviting me. I wish, again, as I said, I wish I were with all of you in person, but as Aninda said, God knows when that's going to be, but I hope it'll be very, very soon that we can be free to travel. So I'm going to give a set of 3 lectures on some of the most recent experiments in a way that I've been doing with machine learning. I'm very much a newcomer to this field of machine learning, but I think it's a very fun way to do theoretical physics, to do string theory, and to do mathematics. What I'm going to do is I'm going to divide the talk into 3 parts, and I'm going to introduce Calabi-Yau manifolds, and this is something perhaps most of you are familiar with. But what I would take a slightly different take on Calabi-Yau manifolds. Not because this is a lecture on Calabi-Yau compactification or all that, but what I want to emphasize, the take-home message is that Calabi-Yau manifolds, in fact, all of algebraic geometry is an image processing problem. So this is a very sort of a mystical way of looking at algebraic geometry. But because I want to be very concrete, and my favorite part of algebraic geometry, and indeed of string theory, is Calabi-Yau manifolds. I'm going to introduce Calabi-Yau manifolds in a way to make it explicitly emphasizing on the data structure of Calabi-Yau manifolds. So in that sense, so of course, as physicists, you may want to take this as you want to see the landscape of Calabi-Yau manifolds as a microcosm for the string landscape. But I also want to emphasize that it is also a microcosm of the mathematics landscape. So these are going to be very concrete. We're going to make, in fact, in my second lecture, my second or third lecture, I think I'm even going to start using some coding. Hopefully this is going to work online, and I will show you some codes because this is a very hands-on thing. In part 2, I'm going to give an introduction to machine learning, to what I call machine learning 101, which I'm really, in some sense, that's all I'm qualified to give, because I don't think I know machine learning beyond machine learning 101 myself. I only recently learned about this stuff, and it's kind of fun. And part 3 is about having fun. And I'll tell you some of the experiments you can do. And I want to emphasize that, pretty much all of mathematics can be taken. And I think the entire structure of what we call mathematics can, in some sense, be fed into some kind of machine learning paradigm. So I want you to take whatever your favorite problem is and try to use some of the techniques that I will introduce. And in the tutorials, My students Jia Kambao and Edward Hurst very kindly agreed to give you some tutorials, and so they're very much Python people. So we'll hopefully in the tutorials they'll give you some very hands-on experience with Python TensorFlow. It's kind of interesting that people use Python TensorFlow and Keras have become sort of the standard industry. If you want to get a job anywhere these days, they very much ask whether you have experience with Python. And if you want an analytic job, they often ask you whether you have any experience with Python TensorFlow. So that's and it's kind of interesting. What I'm borrowing is sort of that linguistics of that world into our research, which is theoretical physics and mathematics. So if you want to read more about this, here's a shameless self-advertisement. You can read about much of these lectures in this book, which just came out in the summer. Buy this because I get royalties. And so this is about a 250-page version. And if you want a quick 20-page version, you can read this you can flip through this preprint, which I put on the archive. So let's begin with part one. I just want to introduce to you, sort of why Calabi-Yau manifolds, not so much for the sake of algebraic geometry or even for string theory, but just to emphasize the fact that what we're doing here is very concrete data, but it came from a very, very ancient problem. So let's forget about physics for a minute. Here is a classic problem in mathematics, right? That goes back at least to Euler and to Gauss and to Riemann. So what did these guys do? Well, they were studying two-dimensional real manifolds, right? They were for all our purposes, we're going to take compact, orientable, two-dimensional manifolds without boundary, just to be very concrete. I'm going to get so Euler realized, of course, is that the topology type of this is classified by a single number, what we call the genus, the number of holes. And there is another combination, which is 2 minus twice the genus, and that's what we call the Euler number. Okay, so why do you take 2 minus 2g? Well, that's because that's Euler. So the Euler basically put topology and combinatorics, if you wish, at one level. But why 2 minus 2g? Well, that's what Gauss called his theorema Grigium, because what you do is for these objects, you can define Gaussian curvature. And if you integrate that Gaussian curvature over this two-dimensional manifold and divide it by 2 pi, I think it's 2 pi, not 4 pi, 2 pi, you're going to get 2 minus 2g. So that integer, that non-negative integer, is named the Euler characteristic in honor of Gauss, in honor of Euler. So that's kind of interesting. So here I've listed, this is all very familiar to you, but I just want to emphasize what is interesting is that there's a trichotomy to this classification, that Euler 0, in this case, is genus 1, but 2 minus 2g is 0, and this is the Ricci flat case. Everything to the left is called, well, there's only one case to the left. Well, it's the sphere, which is positive curvature, right? In fact, it's constant positive curvature. This is everywhere 0 curvature. You can actually see why the torus has 0 curvature, because you can just fold a flat piece of paper once and twice, right? And everything above here, for genus greater than 0, you have Euler number less than 0 because of 2 minus 2g. And these are negative curvature objects, right? So they're hyperbolic geometry. So this is essentially spherical geometry, Ricci flat, and hyperbolic geometry. So what I want to emphasize is this middle column is right at the boundary because of Gauss's theorem of what is considered positive curvature and what is negative curvature. This Ricci flat case, I'm not using the words Calabi-Yau, I'm just saying this is somehow a very interesting boundary case. So that was Euler and that was Gauss. And what about Riemann? Well, Riemann, of course, is famous for his introduction of complex ideas into mathematics. And what Riemann realized is that all of these things are actually complex, what we now call complex manifolds. These things have complex structure. So, and this trichotomy theorem, in the sense of Riemann, is then the famous Riemann uniformization theorem, that you can not only just think about these as real two-dimensional manifolds, but you should think of these as one-dimensional complex curves that can descend essentially by certain quotients of the upper half complex plane. And so that's a very beautiful result, that you can think about these as one-dimensional complex manifolds that obey this uniformization theorem of this trichotomy. Okay, so that's, I mean, I guess this is 200 years of geometry in its various guises, right? So, and again, because now that's it. That's the only time I've actually mentioned real manifolds. From now on, we're only going to be thinking about complex manifolds. Okay, and the point is, in complex geometry, this Ricci-flat case bounds what we call the left-hand side is what we call Fano varieties, and everything on the right-hand side we will call varieties of general type. That's actually a very interesting sort of structure. Once you put this complexity into it, this middle column is also the boundary case of Fano, which is positive curvature complex manifolds, and general type, which usually do not admit very good classification. So I know we already see in dimension one, complex dimension one, there's an infinite family here, but complex varieties of general type are very, very difficult and very, very worldly. And it is true that Fano varieties, so of course, we know that S2 in the complex sense is CP1, and CP1 is the Fano curve, the Fano complex curve. And that Fano case, usually in every dimension, Fano varieties have some kind of finite topological type of classification. The middle case, again, I want to emphasize this middle case of Ricci-flat, zero Ricci curvature, a case for complex varieties, we don't know. But it is still a belief of Yau's that they also would admit some kind of finiteness results. So this is why in complex geometry, this trichotomy is also interesting in sort of the classification of algebraic varieties. Okay, so we can rephrase all of this in a nice little diagram, right? For at least for complex dimension one, right? So for surface for real surfaces or complex algebraic curves, right? So we can do so sort of this diagram. Yes, I see something on the chat. Yes, absolutely. All of the slides will be made available. So I think this is fine. So this is Euler's result on topology, right? And this is Gauss's result, which relates topology to differential geometry. I mean, this is actually really amazing if you think about it, right? Why should there be a continuous integral of an analytic object which gives an integer that controls topology, right? This is why Gauss called this theorem, the equivalence of this bit and this bit, his theorema egregium, his great theorem. This is Gauss's great theorem. So if he's proud of it, I think we should all probably just bow down and worship it. Right. So, and let's see the next thing. Sorry, I'm having problems doing. There we go. Sorry, I'm trying to move my floating window. Though somehow I've touched something. There we go. So, so that's Gauss relating topology to differential geometry. By relating curvature, which is an analytic object, to topological invariance, which is an integral object. And so this is 18th, 19th century. Now, because of Riemann, we can make all this very, 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 very cool and cute. And because of Chern, and then the French school, the Bourbaki school, we can phrase this in a more sophisticated language. This integral of this analytic object called curvature can be thought of now in modern algebraic geometry as an intersection of forms, right? So this is the intersection pairing of the surface with its curvature. So this integral in modern algebraic language is this intersection of a homological object, which is this algebraic cycle of the surface, with a cohomological object, which we call the Chern class, right? So this intersection parent is this. So now we get into the theory of characteristic classes. And because of the topological invariance of characteristic classes, we can sort of explain in some sense the integrality of the Euler number. Now, what about, where does this come in? Well, if you think about what the Euler number is, and then that's Euler's grade inside, it's kind of really, really pretty because he did this even before. So what Euler taught us to do is that if you take any convex polytope drawn on a sphere, so you just take a polyhedron, right? Now, these are many-faced objects. Take like on your favorite polyhedron, a cube or something, or a pyramid. If you take the number of zero-dimensional objects, points, subtracted by the number of one-dimensional objects, lines, plus the number of two-dimensional objects, the faces, you're always going to get 2, right? You know, take the tetrahedron. You've got 4 vertices. You've got 6 lines. Sorry, 1 and 2, 3. Yeah, you've got 6 lines and 4 faces. If you do 2 minus 6 plus 4 minus 6 plus 4, you get 2, right? You do this to any convex object on the sphere, you'll always get 2. If you do any convex object on the torus, you'll get 0. So that is purely combinatorics. Well, where does that plus minus come from? In modern algebraic geometry, that comes from this alternating sum, and that is the content of the index theorem. So this is the insight of Atiyah and Singer, and Prodi. And why is this? It's because you have this alternating sum in homology and cohomology. Why alternating sum? Is because you have exact sequences, right? So you have kernels and co-kernels, you subtract plus minus, right? The cohomology is defined by Kerr over M, and this top and bottom division is what gives you the plus minus sign. So this is a very beautiful story. So this is a one single diagram in some sense that summarizes 200 years of geometry, all the way from algebraic topology to differential geometry to modern algebraic geometry. So this is really, really nice. And what I want to emphasize, of course, this is not a lecture course on algebraic geometry, nor is it even a lecture course on string theory. What this is a lecture course is that this diagram and generalizations of this diagram can be put, and this is the take-home message, can be put and phrased in the language of modern data science, because everything here is not just abstract, but algorithmic. And that's what I want to say. Every single problem in algebraic geometry and beyond, and I will get to the beyond in the third lecture, can at some level be phrased into some kind of a tensor manipulation problem. And tensor manipulation problems is exactly what is good for machine learning. And that's why it works. Okay, so that's the take-home message. So I've introduced these words. At some level, since this is a fairly advanced group of students and researchers, I think you all have familiarity with Chern classes and Betty numbers and whatnot from a formal perspective. But what I want to say that there's an underlying history why these things come about. And one last thing is the Hodge number, which is all it is because of Riemann, you have complexified, these topologies. You've complexified these geometries, and complexification allows you to double index, right? The holomorphic and the non-holomorphic. And the Hodge number that's exactly what it is. It's the holomorphic and anti-holomorphic, if you wish, pieces of the Betty number. And this is why the Kuhneth version of the Hodge number satisfies this sum rule. So HI is the Betty number. And so the Betty number, because you have complexification, splits into complex and into holomorphic and non-holomorphic pieces. So that's the background of 200 years of geometry. So how do all of this stuff? So what about higher dimension, right? You want to ask, how do we generalize this beautiful story that I've written down for complex dimension 1, right? You obviously want to go to higher dimension, but higher dimension is very, very difficult, right? If you just think about something like the Poincare conjecture, that took years and years to settle. Well, luckily, for a very special class of manifolds, complex manifolds, namely the Kähler ones, we have a version of this. I'm not saying that for non-Kähler ones we don't have something like this, but at least certainly for Kähler ones, they are this diagram can somewhat be generalized. So since this audience might be slightly mixed, I'm just going to give you one line just to refresh your mind on what Kählerness means, right? So here's just everything I've said is everything that is standard. I will say fairly quickly, and then when I get down to nitty-gritty details of the data construction of Calabi-Yau, I'll slow down. So here's a sequence of specializations where I've talked about a real manifold. You can put a Riemannian first. This is a sequence of specializations. First of all, Riemannian structure. Positive definite symmetric metric. You can put one more structure, complex Riemannian, namely you put you allow the existence of holomorphic and anti-holomorphic forms, and then you put Hermitian structure, which is such that only the mixed indices survive, and finally you just shrink this Venn diagram. Finally, you get to Kähler, which is that there's the existence of this two form, which is closed. This is equivalent to saying that your metric, your Hermitian metric, your mixed index metric comes from a double derivative, dd bar, of a single scalar potential. So this is just a refresher of what Kähler means. So you really need to go through 4 levels of specialization to get to Kählerness, right? Which can be thought of as simply your metric comes from a single scalar function. Okay, so let me go here. And just to refresh your mind again, on the Riemannian fold, already at this level of Riemannian manifolds, the existence of the positive definite symmetric metric allows you to define a Laplacian. It's a bit messy, right? Which you can define through the Hodge star, right? So this is standard stuff. And specializing one more on Hermitian, which is this double index object. Right, you can generalize the Laplacian, or you can rewrite the Laplacian as dd dagger, right? And finally, on the Kähler one, this Laplacian simplifies even further, and to just dependent either on the del piece or the del bar piece, and because of this simplification, you have the Hodge decomposition of the usual cohomology into this double index object. Okay, so this is of course standard, so I don't want to belabor the point. So this is just the sequence of specializations. So what's the point of all of this? Well, the point is that whenever you specialize in mathematics, you're going to get simpler, and you're likely to get better results, right? The more restrictions and more structure you put in, the more likely you're going to have very pretty and simple results. So generalizing this diagram to higher dimension for general manifolds is very difficult, but at least for Kähler, we do have something like this diagram, and that is the content of the Calabi conjecture, which came out in 1950s, right? So the conjecture itself is boring because there's some technical result which says for compact Kähler manifold with G and this Kähler 2 form that I mentioned, and given a Ricci 2 form, which is in the same cohomology class as C1, then there exists a unique a metric and determining this unique Kähler 2 form, such that the 2 form this twiddle is in the same homology class as this, and such that the Ricci curvature given from this is the requisite R. Okay, so that's a whole lot of mouthful. What is the content of this conjecture? Well, it is exactly the generalization of this diagram, right? What it's saying is, just like for surfaces in complex dimension 1, C1 should control, this Chern class should control your curvature, right? And that's the point. The intersection theory in algebraic geometry, this is a purely algebraic object, should control something that is differential, right? That's essentially the content of this conjecture. And it turns out to be very, very difficult. And we know that the special case of surfaces certainly works. Well, if you think about it, in complex dimension 1, right? Once you got this G mu nu, because surfaces, Riemann told us that Euler-Gauss's two-dimensional surfaces are Riemann surfaces, right? They're called Riemann surfaces. They're complex, so they're complex objects. They're complex dimension 1 objects, and because they're real dimension 2, if you have a 2 form on it, your d of that would just be 0 automatically. In other words, all of these things are in fact Kähler. So for this diagram that we're back to complex dimension 1, the Calabi conjecture certainly holds, right? So that's why Calabi was thinking about this. He was trying to generalize this beautiful story to higher dimension, to arbitrary dimension, a complex dimension of Kählerness, right? So in particular, if the first Chern class vanishes, you have Ricci flatness, right? That's exactly this statement. Well, we know it certainly holds for complex dimension 1, the Riemann surfaces, right? That's this case. But the point is, the Calabi conjecture says that this should hold for all dimension. And in fact, it should hold not just for the boundary case, but also for final varieties and varieties of general type, as long as they're Kähler. Now, you say, well, maybe since I've put so many restrictions on Venn diagrams, right? Maybe there aren't that many Kähler manifolds, because I've put too many restrictions. But Kähler is actually extremely common in the following sense. I mean, if you think about what algebraic geometry is, well, the vast majority of complex algebraic geometry is about studying complex polynomials in complex projective space. Now, complex projective space is Kähler. So any subvarieties defined by holomorphic polynomials inside that would also be guaranteed to be Kähler. So the vast majorities of things we ever think about is essentially Kähler anyway. So it's not, what I want to say is that we're not talking about a tiny little corner of the landscape of possible manifolds, but we are talking about the vast majority of algebraic geometry, because algebraic geometry is about studying vanishing polynomials or systems of polynomials in complex projective space. So I'm going to get to that in more detail shortly. So, I mean, Calabi immediately proved the uniqueness bit of this, but the existence was so difficult, it had to wait for another 20 years before Yau proved it, using some very fancy harmonic analysis on Monge-Ampère equations. But how do you know such a solution exists? I mean, at the end of the day, this statement will be translated into a set of very highly nonlinear PDEs, and you got to show and prove the existence of solutions of these PDEs. So Yau showed this, and he was immediately awarded the Fields Medal, right? So you can see why this is important, because for mathematicians, this set of conjectures is a continuation and generalization of something that goes back to Euler, Gauss, and Riemann. So that's why it was a central part of mathematics, and that we had to do this, right? So Yau was very happy because he got the Fields Medal for proving this existence. It's very, very technical and tour de force proof of the existence. So henceforth, I'm going to call these Kähler-Ricci flat objects Calabi-Yau. In fact, the word Calabi-Yau did not exist even when Yau got the Fields Medal. Mathematicians are very humble. They don't name things after themselves. When he got the Fields Medal for this, these Ricci flat objects were just simply called complex Kähler-Ricci flat manifolds. So where does the word Calabi-Yau come from? Well, that actually comes from physics. The actual word was termed by physicists. So far I have said absolutely nothing about physics, right? So this is just a précis of 200 years of geometry and why it's important that we study these things. Okay, and this is, Calabi-Yau manifolds is certainly my favorite kind of algebraic varieties, and they're very concrete. I'm going to get to them in a minute. So, any questions so far? You can chat it or shout out, but everybody's happy so far?
Yeah, I don't see any raised hands.
Okay, no problem.
So the way to ask questions is to raise your hand just in case you're unfamiliar with Zoom. So there is a tool where called reaction. So reaction in your reaction, you can see that there is an option called raise hand. So you can raise your hand and ask questions. Okay, so there are no questions. You can continue.
No problem. Okay, good. So good. So, that's the state of the art until 1982, right? And in a tradition that goes back to Euler, right? So now, what the hell has this got to do with physics, right? So it's kind of interesting that this thing came out naturally in what we call string phenomenology. So I will again very quickly go through it. It's because I think a lot of this is very standard. So, I'm not going to emphasize this again. String theory is this theory that unifies quantum gravity and general relativity in 10 dimensions, and we live in some 4-dimensional manifold. Let's assume that it's maximally symmetric. So your Riemann tensor can be written in this form, and your Ricci curvature, this R, is 0 for Minkowski, positive for de Sitter, and negative for anti-de Sitter, and you take 2-dimensional reduction scenarios. You can take your extra dimensions to be small, or you can take the large, some kind of a brane world setup thing. And you do want supersymmetry at an intermediate scale, somewhere between the string and electroweak scale. And so what we're after is looking for some kind of classical vacuum of string theory from these 10 dimensions that preserves n equal to 1 supersymmetry in 4 dimensions. Right? So at least this was the beginning of what people were thinking about. Note the date on this, right? So this was already, the branes were not known to this at this point, but the date on this, which I'm going to get into, also happens exactly to be mid-80s. I'm going to show that in a minute. So it's just, they're two completely different paths, right? Why would Yau ever talk to a physicist, at that time? But very interestingly, I'll tell you a bit of historical reason. So somebody chatted me a question. Oh, references on this, but okay, great. Aninda's very kind in giving references to that already, great. So, and the date, of course, is 1986, right? Not 1984, but 1986 came about from very shortly, 85, 86. This is roughly 86. So somewhere between 84 and 86 was the first string revolution, because of the partly because of the realization of the heterotic string, which had in it the natural E8 gauge group. All of a sudden, string theory became not just a theory of quantum gravity, but because of E8, and E8 has within it a subgroup of the standard model group, SU3 cross SU2 cross U1, through a sequence of gut groups like SU5 and SO10. It was thought, well, actually, maybe it's not just a theory of quantum gravity, but it could also be a theory of particle physics, right? So not just the string spectrum of all sorts of particles, but actually standard model particles. So that was this seminal paper of 86 of Candelas, Forrest, Stroman, and Witten. What they took was, they took this heterotic Lagrangian, and of course the heterotic string was discovered by the string quartet, Gross, Martinek, Harvey, and Gross, right? I think just like a few months before. So they took this effective Lagrangian for the 10-dimensional heterotic string. And the details again are not important. What they do is you take the SUSY variation equations for this. So for the gravitino, or there's in the heterotic string you have the dilatino, the lambda, the gravitino, and the adjoint Yang-Mills field, and some kind of Bianchi, and of course, a Bianchi identity. So you just write down the SUSY variation of this Lagrangian and set it to 0. So you want to preserve supersymmetry. And so here's again, now comes to a point with, again, a sequence of specializations. To solve this is not easy. So this is called the Strominger-Hall system, after Strominger and Chris Hall. And it's not easy, right? These are multi-indexed objects, and you can't solve it in complete generality. But at least you can specialize for certain cases. For example, you can set the three-form field to 0, right? And that gives you the Killing-Spinner equation. So you've set this to 0, right? Now remember that we want to split the 10 dimensions into 4 dimensions, 6 dimensions. I'm going through this very quickly because this is in Green, Schwartz, and Witten, right? It's all in there. So I mean, again, this is not a course on this. This is a course on machine learning. I just want to very quickly go through this. So your external space constraints is what they took was Minkowski, but of course we really should be looking for de Sitter. But Minkowski 0 to first order is okay because it's tiny little cosmological constant. So we just solve. Let's look for the R equal to 0 solution. So at this point we already made three generalized. I mean, at least three assumptions in solving the Strominger-Hall system. We've assumed the three-form field in the three-form field to be 0. We've assumed maximal supersymmetry, and we've assumed Minkowski, which is fine. You can, of course, generalize this, and this is still a very active field. I'm not involved in this field, but just sort of solving the system. So your internal space then is, because of your vanishing of your external space, you're looking for Minkowski, you're looking for Ricci-flat internal space. So that's the origin of the Ricci-flatness. In other words, what these guys were looking for is what happens when you're solving vacuum Einstein equations, right? This is fine. So of course, vacuum Einstein means Ricci-flatness. And then basically this setup tells you that you can split up the compact directions, the compact 6 directions, and still maintain this Ricci-flatness. So very quickly, this 6-dimensional manifold is not just any manifold that is Ricci-flat, but it is also a spin manifold, because its holonomy group is not just the general SO6, but in fact SU4. And this covariant constant spinner equation, right, wants you essentially to find a covariantly constant spinner, right? So what that means is that this 6 manifold has SU3 holonomy, not just SU4, but lives in particular with this one more condition where you can think of this, the not just any spinner, not the existence of any spinner, but a covariantly constant spinner, which restricts the holonomy further from SU4 to SU3. So the upshot of this is that you can write down. In fact, you can explicitly write down this combination. Again, this is in Green, Schwartz, and Witten. You can write down this combination for the internal internal spinner, and that gives you the J-mu, the almost complex structure. So what these guys realized is not only is this internal manifold, again, I emphasize, up to these assumptions, right? The vanishing of the three form, the assumption of maximally supersymmetric external solution, and Minkowski, in fact, solution would restrict your internal manifold to be exactly this condition, not only Ricci-flat, but it is in fact Kähler with SU3 holonomy. Okay, I'm not going to bore you with it, but you can see this in the appendix, how you can show this. So this is basically a one-page summary for those who want to read more about this. So this is basically a one-page summary of the standard literature. So right? Let's take stock and see what we've done here. So physicists wanted to look for they wanted to look for supersymmetric four-dimensional maximally supersymmetric Minkowski space solution from the heterotic string, which was just discovered, right? And that solution, under this set of assumptions, gave rise to them a condition. I mean, of course, physicists didn't know what Kähler manifolds are at that point, but they knew, well, whatever these things are, they're in fact complex manifolds such that their metric comes from a double derivative of a single scalar potential. Right? So that's kind of interesting. So what are these objects, right? So, well, it just so happens, right? I mean, look at the dates, it's perfect, right? 84 to 86 was when physicists were just, doing this from a completely different perspective, right? Because people were trying to look for vacuum solutions of string theory. And 82 was when Yau proved that this family of Kähler manifolds had this very beautiful structure that generalizes Euler, Gauss, and Riemann. And it just so happens that Strominger was visiting Yau. I don't understand, I don't know particularly the reason why Strominger was visiting Yau at that point, but Strominger was visiting Yau at the IIS from 84 to 86. And when this paper came out, Strominger, but this is a story that Philip Candelas tells me, so this is from first source, so I can trust it. And Philip is a fantastic storyteller. So what happened was, Yau was next door, and then these guys stumbled upon this very peculiar condition that you have a complex manifold whose permission metric comes from a double derivative of a single scalar potential such that the Ricci curvature of that vanishes. Right? So what are these things? So Strominger goes to Yau's office and said, well, can you tell me what these things are? And Yau says, well, actually, I just got the Fields Medal for it. So that's fantastic, right? And I told him what these are. So it was actually at this point that the physicists, these four guys, named these Ricci flat Kähler manifolds to be Calabi-Yau in honor of the Calabi conjecture and Yau's proof. So this is kind of nice that this is a great contribution from physics to the math literature. Before this, the word Calabi-Yau didn't exist. So that's kind of fun. So let me just summarize before I actually get into the nitty-gritty details of Calabi-Yau. Again, I'm using Calabi-Yau only as a point of illustration of why there's so much data on this. So here's a list of possible equivalent definitions of Calabi-Yau threefolds. Okay, threefolds, for example. First of all, it's Kähler vanishing Chern class, right? This is, so see, the equivalence of the first two is exactly what I've been trying to emphasize, right? That Chern class controls curvature, right? That's the content of the first line, right? And then this special holonomy thing, which I won't actually really need, is due to Berger's classification of when what kind of manifold you have when the manifold of type, it's an if and only if condition by just looking at the holonomy when you do parallel transport. So this is a nice point. So you see Calabi-Yau somewhere in between Kählerness and hyperkählerness and quaternionic Kählerness. Okay, so I won't need that. An equivalent condition you can show is the existence of the global holomorphic, nowhere vanishing holomorphic three form. So that's the volume form, right? If you tensor it, you get the volume form. You can integrate these things. And I don't even think I'll need any of the other stuff. So in other words, it's kind of interesting. I told you that pretty much anything you will ever see in algebraic geometry is Kähler, because you're just doing vanishings of polynomial equations. So the Calabi-Yau condition is nice because you can just consider the subclass of vanishing first Chern class. And so we're going to see examples of this in a few slides. the point is, this part is differential geometry here. And curvature is messy, right? It's got, you know, the curvature 2 form is a two index object. And if you write it out, it's a huge mess. But because of the Calabi-Yau theorem, this thing is equivalent to this. Computing C1, and I will show you shortly, is relatively simple because it's purely algebraic. You know, there are no integrals. There are no integrals involved other than intersection theory in integrals. Now, all you have to do is algebra. That's the point. That's why we call algebraic geometry, right? Because you can reduce its computations to algebra. And that's very much amenable to the kind of thing that I'll be talking about. If you want to do this to curvature, you can do, but that involves in like kind of messy integrals, right? So yeah, c'est la vie. So let me pause again for a second for any questions. Everybody's happy so far? Okay. Okay, good. So it's kind of interesting. In the mid-80s, 2 directions merged, right? From one is a 200-year-old tradition in geometry, and another one is a 20-year-old tradition from particle physics, right? Remember, string theory came out from like, you know, dual resonance models trying to explain the behavior of hadrons. But somehow these 2 converged around about 1985. And suddenly physicists, for the first time, were talking to algebraic geometers in a very serious way. Physicists have been talking to differential geometers since Einstein, right? I mean, that was Einstein's insight, but not so much to algebraic geometers, because, you know, that's got to be a bit obscure. Physicists really like indices and integrals, but suddenly we needed to go into intersection theory of algebraic forms. Why? Because of this story that I'm trying to emphasize. Good. Somebody asked a fantastic question. Does the algebraic nature make it easily for translate? That's exactly the point of my the remaining of this lectures. The reason I wanted to, well, I won't answer that question. Yeah, so the question is, does the algebraic nature make it easily for translating into a machine learning problem? Absolutely. That's what initially got me thinking into this problem, because of the, and I will show you in a minute, well, not in a minute, in the second lecture, that the algebraic structure well, I'm going to make an extreme statement. Algebraic geometry is about tensor manipulation. And I will show you why this is the case shortly. However, now I've thought about this a little more. You can, in fact, translate any problem, not even in differential geometry, into this language if you're clever enough with your data representation. So actually, I just wrote a paper with Juan Ipiña, who's a very good. I mean, he comes from the GR background, about how to do machine learning of classifications of metric types. So you can. But certainly what initially got me thinking, at least in 2017, about it was because the algebraic nature of the problem was very, very much amenable towards the data representation I want to talk about. But so stay tuned. So it's nice that I've been doing algebraic geometry as I was growing up, as I was growing up, because if I did differential geometry, it would have been harder for me to at least have thought about, because that translation is not as natural. But once you have algebra, it's all cool. So stay tuned. That's a very good question. So just to introduce you a few more buzzwords, really, just, I mean, in terms of the mathematics. And then my second lecture is going to be about buzzwords in data science. So first of all, I said the Betti numbers can be complexified into Hodge numbers. So that's the content of Hodge decomposition. You know, this Kuhnert formula of Hodge decomposition. There's nothing, that's nothing mysterious. I mean, to prove this is very difficult because you need to prove Hodge decomposition. But essentially, you know, a hand-wavy understanding of this, well, just, of course, this is true because this is just, you know, double index object, and what else can it possibly be? Okay, that's your one line physics proof. So there is complex conjugation because we're dealing with complex manifolds. So that automatically makes HPQ to HQP. Again, everything I've said here is it's compact, smooth, no boundaries. So these things will actually go through. There's the Hodge-Star condition, which is essentially Poincare, the complex version of Poincare duality that makes this happen. So for Kähler manifolds, you can organize the Betti numbers into a two-dimensional array called the Hodge diamond, right? And the Hodge diamond obeys these two conditions. So it's this flip, top-down flip is complex conjugation. It's Poincare duality, and left-right flip is Hodge-Star. And we're going to if you consider only compact connected ones, so there's only one, there's constant functions. This is even one. This is one. And if you consider simply connected, the fundamental group is 0. So H1 is 0. So that makes this 0 and then this 0. So very quickly, you can see that the Hodge diamond can't be too complicated. Finally, this is even 1, and this is even 1 because there's only a unique holomorphic 3 form. Right? So in other words, if you're dealing with a connected, simply connected, smooth, compact Calabi-Yau threefold, its Hodge diamond would just look like this, and you don't have much more to do. And you can see immediately there are only two integers. There's H11 and H21, and that's exactly right. And these are the 2 degrees of freedom for Calabi-Yau threefold, assuming connected and simply connected. And we will actually talk about non-simply connected, but a bit later. So the point is, we have a dual pair of integers that characterizes the topological type, okay, the topological type of Calabi-Yau threefold. Okay, so this is kind of nice because this sequence of specializations, this diamond here is the generalization of this, right? Because here, for complex dimension 1, a single integer, the genus, or 2 minus 2g, the Euler number, completely characterizes the topology type of one-dimensional Kähler surfaces, Kähler manifolds. In particular, the boundary case, the Calabi-Yau case, is this torus, this case, right? And that is true. The Calabi-Yau one-fold is just this, the T2. That's the only example. And the diamond is the generalization of this fact, but now we have 2 objects, this one and this one. And they're called H11 and H21. If you really want to know what they are, it's H11 is the Kähler structure. Why is it called Kähler structure? Because this is the Kähler 2 form. This is exactly, this is a 2 form, right? And H21 you can show is the complex structure. This is a 3 form, a 3 real form. And locally, a Calabi-Yau in the moduli space, if you consider the space of a Calabi-Yau threefolds, it is actually a direct product of all possible Kähler forms and all possible complex structure forms. So, okay, this is a very fancy algebraic geometry way of saying it. But what really is, what this diagram essentially says that this integer controls the size of your manifold, and this controls the shape of your manifold. Okay, and we're going to see shortly that by shape, I mean something very, very specific. It's going to be exactly the coefficients of definition in the polynomials in some embedding. Okay, then, okay, we're almost done there now, because then it says, well, what Euler tells us to do, remember, everything horizontal is by dimension, dimension 0, dimension 1, 2, 3, 4, 5, 6, right? So it's a complex threefold, so it's a real sixfold. And Euler tells us to do plus, minus, plus, minus, plus, minus, plus, right? And then each row sum, because of Kuhnith or Hodge decomposition, will sum to the Betti number, right? So if you just sum it all up, you get the Euler number of a Calabi-Yau manifold of this type would just be twice the difference of H11 minus H21. And that Euler number is, exactly this, the 3-dimensional version of this. Right. And indeed, because of Calabi-Yau, we do have this complete story, and that Euler number can indeed be obtained from intersection theory in algebraic geometry, where you take this algebraic intersection of the Chern class with the class of your threefold, right? And we're gonna do that in a minute. So that's fun. And that's all we need. So I think we've gotten all the buzzwords out, right? So we've gotten Betti number, Euler number, Hodge number, right? And the Hodge diamond is just the generalization of that diagram in dimension 1. And I think, yeah, cool. So it's clear, everyone? Everyone is happy? If you're not happy, you can just chat it. If you're shy about raising your arms, or you haven't found out where the raise arm or raise hand button is, I haven't found where it is. So just type into chat, which is totally fine. Okay, and fine, everybody's happy. So finally, we get to this explicit part, right? And I said, I'm not teaching you Calabi-Yau manifolds. I'm just showing that this stuff is very, very concrete. Right? So as I said, in complex dimension 1, this is it. It's S1 cross S1. That's the only example. It's the surface of a donut. I love the chocolate part of the donut, by the way. In complex dimension 2, there is the 4 donut, the S1 cross S1 4 times. And then there is this strange outlier, which is a beautiful thing, which deserves a 5-hour lecture by itself, called the K3 surface. I'm not going to really talk about K3 surfaces, but they're just, this is it. So you would think, well, how many possible threefolds are there? Well, we have absolutely no idea. This is a very bizarre sequence in mathematics. You usually go 1 and 2, maybe 3, but no, this is 1, 2. So far, to give you an idea, we know at least 1 billion of these. By a billion, so now let me quantify. What do I mean by a billion? I mean 1 billion in the sense of topological type. All right. So I lied to you a little bit in the sense that the topology for Calabi-Yau one-fold, the Riemann surfaces, sorry, not Calabi-Yau, but just scalar one-folds or Riemann surfaces is really uniquely characterized by a single integer, the genus or the Euler number. That's it. However, for Calabi-Yau threefolds, it's a little more complicated. I've told you there that the Hodge diamond, this pair H11, H21, and therefore the Euler number is the version, it's a three-dimensional version of this, but the story is a little more complicated. You also need to specify the Chern classes and the triple intersection numbers. So C1 is 0, so we don't need to worry about it. C3 is the top Chern class, and we know that integrates by intersection to the Euler number, so we don't need that either. But C2, the middle, the 4 form, that's a little complicated. And that for each Calabi-Yaus, they're different, and they are topological invariants. So you do need to know H11, H21, C2, and in addition, you need to know how all possible curves intersect. So there's a triple pairing of curve classes, and that's what's known as a triple intersection form. So sort of H1, H1, H1 paired up to H3, and that's a 3 tensor, KIJK, meaning all possible pairings of curve classes. But that's enough, right? These integers, and they're all positive integers, non-negative integers. These things will uniquely classify the topological type. So that's what I mean by this number. We have no idea how many possible such numbers there are. So, and I think that goes a little bit back to Bavai-Tiagi's question. Yes, it's because of this, right? H11, H21, and KIJK, C2 as a vector, and it's a very specific data structure that specifies the possible topologies of Calabi-Yaus, but we don't know what it is. We have no idea. It is a conjecture of Yau that in every dimension, the Calabi-Yau case, the topological type of Calabi-Yau case is finite, but this is an open conjecture, we don't know. In dimension one, you see it's obvious, right? In dimension one, there's only one case, so it's finite, fine. But in dimension three, we already don't have such a result. And it will be very nice for someone to prove it, and will be a very beautiful proof. Somebody probably get the Fields Medal for it. It is a theorem that the funnel type, positive curvature, is finite type, in the sense that there's only a finite, in every complex dimension, the number of possible funnel varieties in topology type is finite. So this is not a boundary. So Yau's hope is that the boundary case of the Calabi-Yau case is also finite, and it is well known that general type is unclassified. It's infinite, and I think unclassifiable in the sense that there is no scheme by which you can even begin to classify surfaces of general type. I think that may be one of those MP or Turing incomplete problems that don't bother. This is unclassifiable. So there we stand. So it kind of really sucked for the physicists, right? Because as far as physics is concerned, right? If you do one-dimensional geometry, d equal to 1 would give you an 8-dimensional universe. D equal to 2 would give you complex dimension 1 is 10 minus 2. That's an 8-dimensional universe. D equal to 2 will give you a 6-dimensional QFT. It's the D equal to 3 that gives you the 4-dimensional QFT. If we lived in 4 dimensions, at least within this setup, all we needed to check is string theory on T4 and K3 to see whether they give anything close to the real world. If not, then it's out. But we kind of suck exactly at this boundary case of complex dimension 3. We don't even have a classification result from the mathematics, so we can't even scan through it. And that's part of the thing I want to address shortly. So fine, I know it's life. So let's get down to the nitty-gritty details of actually how to construct this. Again, the point I want to emphasize is how we're going to construct this is what will partially answer some of the questions that's been appearing in chat. Is why is this a data science problem? Okay, so let's just get down to the ground. Well, as I said, what is algebraic geometry? Well, algebraic geometry is about studying the vanishing loci of polynomials in multivariables embedded in, say, Pn. Now, why you say CPN, right? Again, I'm going to, by P, I mean CP, right? Everything here is complex. You can certainly do algebraic geometry in RPN, that's fine. You can do complex algebraic geometry. You can do algebraic geometry in RN, which is, called affine algebraic geometry. That's no problem at all, but, we want complex, we like complex. And why do we like complex so much? Well, because, we like complex because from a physics point of view, it came out here, right? This set of conditions, the existence of spinor and covariant constant spinor conditions led to complex. But from a mathematical point of view, why do we like complex? Because complex is an algebraically closed. The complex number is an algebraically closed field. In other words, you can do algebra, you can always find solutions, right? If I do real polynomials, systems of real polynomials in Rn, I'm not guaranteed I will always have loci, right? But if you do it over the complexes, you're always guaranteed to have solutions somewhere, right? Because of the fundamental theorem of algebra. So this is why I like algebraic geometry so much in CP, in C. Now you say, why CP? Well, because we want compact. That's the only reason. We want to add the points in infinity. Well, that's what CPN is. You take Cn and you bring in the point at infinity as Cn, and you put to make it compact. So in a nutshell, what is algebraic geometry? In our context, algebraic geometry that's all it is. It's about the study of the loci of a system of n plus 1 polynomials in CPN. Okay, that's, you know, this is a sort of thing you can I mean, this is high school algebra in some sense. Well, it's true because you know, it's kind of funny. The sequence of education for theoretical physicists have always been, you study differential geometry first, and then you study algebraic geometry, right? But if you really think about it, the order should be different, right? Because you can do algebraic geometry without learning calculus. You don't need calculus, right? Differential geometry needs calculus. You know, when you talk about, you know, your tangent bundle, you need this d, the d by dt. You know, you need this d. But algebraic geometry is exactly what we studied back in in primary school. Cartesian coordinates. You take Cartesian. Well, okay, fine. You don't do Cartesian coordinates in Rn, but you do Cartesian coordinates in CPn. But there's not just one condition. You bring some infinity point at infinity, and that's it. Then you just study the vanishing loci of the systems of polynomials, and that's all algebraic geometry is. And if you think about it, this is actually a very, very good data structure, right? So. And in fact, this is true in general, right? And so this is the content of the embedding theorems. You can always find a sufficiently large enough pk for Pn for n large enough, such that every algebraic variety can be done by some kind of intersection of polynomials in that sufficiently high Pn, right? And that's always doable. But the n could be very, very large, and you could have very, very many variables, right? But at least it's at least algorithmically statable what every manifold is, or every complex manifold is. So let's do baby case number one. Let's consider what's known as a complete intersection. All that means is, let's start with a single PN, CPN, complex projective space. And I'm going to define it by K polynomials. Okay. If your ambient space dimension is 3 times, so it's 3 more than the number of defining polynomials, and you want to define a threefold, a complex threefold, then great. In this case, it's called complete intersection, because what that means is that every polynomial you define slices out 1 dimension from, you know, it reduces 1 degree of freedom. So you do it 3 times. So you do it k times, that will reduce it exactly to the right dimension. So this is the simplest example of an algebraic variety, a complex algebraic variety. In fact, a complex scalar algebraic variety, because Pn, CPn is scalar. And so it's a nice way of doing it. This, again, certainly not algebraic variety is a complete intersection. But it is true that you can always find a sufficiently large n such that any scalar variety, any scalar manifold can be found as a solution of sufficient number of polynomials. But in the simplest case is when these polynomials, the number of polynomials satisfy this very simple combinatorial condition, and that's the complete intersection condition. Okay, so now you've got this ambient CPN, and you've got exactly n-3 polynomials in n+1 complex variables, right? Remember, CPN has n+1 homogeneous polynomials, right? Because CPN is descended from Cn+1, and you quotient by this equivalent relation. Okay, now you get fancy, right? But the point is, this setup has a very algebraic condition for vanishing of C1, right? Remember, how do you compute the C1? Well, the fancy way of saying this is that you compute the canonical bundle of your manifold. But what is that? It's the highest wedge product of the cotangent space. So what is that? Well, that is just, if you take this manifold embedded in CPN, you take D, you know, take Z0 to Zn to be your homogeneous coordinates. You take the highest possible wedge product, right? And that has to be trivial in order for your first Chern class to vanish. Okay. Now on CPN, your canonical bundle is O of -1 minus n minus 1. Right. So for example, it's on P1, the canonical bundle is O of -2. What that means that the transition functions on S2 has degree 2. Right? And the vanishing of that is that because you want this to vanish, you want the degree of your manifold to be n+1. Okay, so let's summarize what I just did there. The point is the adjunction formula for this degree condition says that if you have a manifold which is Calabi-Yau inside CPN, then your degree of your manifold, your defining polynomial, has to be n+1. Right? That's the fancy algebraic geometry language of saying this. Right? But again, the take-home lesson is very, very simple. It just says, if I have n+1 homogeneous variables, let's see, it's Pn, then all you need is a polynomial which is degree n+1. So immediately you have 5 which are complete intersection in a single Pn. Okay, so let's see what these are. The most famous one is this quintic degree 5 in CP4. Okay, so this, well, if you think, wait, this is very, very concrete. What is this object? If you take, so CP4 has 5 complex coordinates, homogeneous coordinates, Z0 to Z4. And if you take any degree 5 monomial in 4 variables, for example, Z0 to the 5th, right? Z1 to the 5th, that's another one. You could also do Z0, Z1, Z2, Z3, Z4, that's another one. Or you can do Z0 to the 3rd times Z4 times Z5. As long as the total degree is 5, that's a possible term that you can write down to define a Calabi-Yau threefold. Okay, so that's kind of nice. So what I'm giving you here, I've given you all possible number of monomials, right? So there's Z0 to the 5th, Z1 to the 5th, and so on. If you count it up to GL to Z, so GL, if you count that up to GL5C, right, because you can redefine these polynomials, you very quickly convince yourself there's 101 possible ways, 101 possible such monomials. And it just so happens, of course, this doesn't actually work in general, so I won't get into that, but in this particular case, it's just this counting actually works. And that's exactly why H21, which I remember I told you is the shape, is the thing that governs the shape of the manifold. There are exactly 101 possibilities of these possible monomials, and that's the 101 different inequivalent complex structures. So what is that? That's the 101 possible coefficients that you can put in front of these monomials. Right. This is a very beautiful story. Sadly, this argument doesn't work in general. You need more sophisticated exact sequences to make work. It is what it is. H11 here is also equal to 1 because there's, this is in a single projective space, and a single projective space, there's only one Kähler class in Pn, so this is just 1. So now for these manifolds, we've immediately obtained what 1 and what H11 is and H21 is just sort of by fiat. It's kind of nice. So this first column, this first row then is our familiar quintic. That's the one that physicists have been talking about and mathematicians have been talking about. It's the first example of the Calabi-Yau threefold. Now let's just go back to the basics again. What is the one complex dimensional analog of this, right? It's the elliptic curve, right? This is something that I deeply love. If you think about what this story is for for a complex dimension 1 Calabi-Yau manifold, what I told you, well, that's T2, right? This thing here. Okay, going back to here. All right. Well, that's T2. So what is T2? What is a torus? Right. If you think about it as a complex variety, what is a torus? Well, it is. Well, let's go back to this theorem. What is the analog of this statement for the torus? Well, the torus can be embedded. So let's do dimension count. Okay. Now, I want to do complete intersection. The simplest complete intersection is called a hypersurface. I just need one polynomial, right? So let's see. Is it possible? The question is it possible to realize a one-dimensional complex object as a single polynomial? Okay. Well, it seems to be possible because if I lived in CP2, that's a two-dimensional complex object, and I had a single hypersurface, so 2 minus 1 is equal to 1, right? That's good. And so what does that mean? It means I can realize Riemann surfaces as a single polynomial in CP2, right? And indeed, that is always possible. Right, but what is the degree of this polynomial? Well, this fancy algebraic geometry tells us the degree just has to be the embedding P2 plus 1 for it to be Calabi-Yau. So what does that mean? Well, that means a degree 3 polynomial in CP2 or a cubic in CP2 should be the Calabi-Yau one-fold. And that's exactly the case, right? We remember what an elliptic curve is, right? An elliptic curve is a cubic in 2 variables, right? Y squared is equal to x cubed plus x plus 1. That's the Weierstrass form. But that's, we probably remember that from some undergraduate course on elliptic functions. Well, but that's exactly the point. But of course, we might not have been told to do this in CP2. We were told to do that in C2, hence x and y. But remember, CP2 has 3 homogeneous variables. It's dimension 2, but it has 3 complex homogeneous polynomials, x, y, and z, right? So you got these 3 homogeneous polynomials and a cubic in 3 homogeneous polynomials, x, y, z. So for example, x cubed plus y cubed plus z cubed plus x squared y plus x z squared, et cetera, et cetera, et cetera. This combination will be your generic cubic in CP2. And that's exactly what a Calabi-Yau one-fold is as an elliptic curve. The other ones also exist. They're called hyperelliptic curves, right? Remember, if you write a higher degree polynomial, say a degree 5 polynomial, you're going to get a genus 2 object, et cetera, et cetera. And this you can actually plot. I think I did this at some point. You take x, y, and z as complex variables. Sorry, let's not projectivize. Let's just take x and y as complex variables, and then write the real part and the imaginary part of both, and write down the cubic equation. Right now, you got four variables. Eliminate one of them through this equation, and just do Monte Carlo and plot out these 3 points. The 3 remaining ones. You just Monte Carlo it out, and if you plot this in R3, you will actually see the shape of a torus. Right? I think I did this at some point, but I encourage you to do this. It's very, very specific, right? That's what this statement. The mathematical statement is very abstract. A cubic elliptic curve in CP2 is a torus, right? But at the end of the day, what you need to do is just to take x and y, write down the real imaginary parts, write down some nice cubic, and then just plot, eliminate, of course, one of the real coordinates, and then you got 3 real points, Monte Carlo that, and you just plot it, you will see the shape of a torus. Right? That's how specific. This is why I love algebraic geometry, because It's just polynomials. I haven't done a derivative, right? This is all, right? So the point is that the quintic is, now I won't be able to draw it, right? Because we're now visualizing 6 dimensions, right? We can't do that. So the quintic is just that, the 3 complex dimensional generalization of this one complex dimensional thing, which is the Riemann surface. The most famous example of the quintic is what's called the Fermat quintic. It's called Fermat because it's a sum of degree 5 objects, SQ. The analog for that, for the elliptic curve, would be the Fermat elliptic curve, which is x cubed plus y cubed plus z cubed is equal to 0. And you can see that's exactly the content of Fermat for 3 variables. That actually is exactly Fermat. Fine. So what I've constructed, this is very, very specific. So I also mentioned to you that there's a C2 which needs to be worked out, and in addition a triple intersection number. But here the triple intersection number is just a single number because h11 is equal to 0. In general, you have a Dijk, a tensor of h11 by h11 by h11, and then that specifies what this is. You can very quickly convince yourself there are 5 other possibilities. Sorry, there are 4 more possibilities for at least how to construct a Calabi-Yau manifold in a single projective space, right? If you think about if you want a complete intersection such that the degree is 1 more than the ambient space, there aren't that many possibilities. You need to satisfy the following conditions. You need the degree here, 5, to be the ambient 4 plus 1. Okay, so that's the degree constraint that will make C1 vanish. You also want 4 minus the single polynomial, the degree 5 polynomial. 4 minus 1 has equal to 3 because you want a complete intersection threefold. Let's do this one. 2 plus 4 is 6. And that's 1 more than the ambient 5. So now you're doing 2 polynomials in CP5, but 5 minus 2 is equal to 3, right? So now you see this is a combinatorial problem, right? How many other words you can do a 3 plus 3? Because 3 plus 3 is 5 plus 1, but 5 minus 2 is 3. And here's, and then you can quickly see the combinatorics here is very, very limited. Again, you know, well, I'm not saying that all Calabi-Yaus, this is all of Calabi-Yaus. I'm just saying that if you put the complete intersection condition, there aren't that many, and you have this very severe constraint. The next one is what's called the tetraquadratic, where you have 4 polynomials, 1, 2, 3, 4. Each is of degree 2 in the 8 projective variables of CP7. Again, 7 minus 4 is 3. Yeah, and 2 plus 2 plus 2 plus 2 is 7 plus 1. So very quickly you can convince yourself there are only 5 possible Calabi-Yau manifolds embeddable as a complete intersection in a single projective space. Right. Immediately when Strominger went to Yau, Yau told him of these 5. You can just write this down, that's it. But the funky thing is, these things, you can fairly quickly argue, I mean, all of these have h11 equal to 1, descended from this single projective space. And h21, you can use some kind of argument that I did before, you essentially counting monomials. For these simple cases like this, you can do it. You can get h21, and the difference of the two is, remember, h11 minus h21 times 2 is the Euler number. But you see, these simple cases have very, very large Euler number. It's just what it is, which at the time wasn't very good for the physicists. It didn't make them very happy. And I will show you in a minute why it didn't make them very happy. But at least in 1986, when Strominger went to Yau, right next door, it's kind of interesting. Yau was able to tell him these 5, and it was kind of interesting that none of them was what he really wanted. For a reason that I'm going to go into now, and then I'll finish up this first lecture. And again, tables like this are great because you see where I'm getting at, right? I'm talking about configurations. I'm talking about matrices, integer matrices, right? This is what started at least getting me to think about, wait a minute, but you know, there's another branch of science that's very good at matrix manipulation, right? You know, your computer says GPUs. GPUs are that's what they're specialized for. They're specialized for matrix manipulation. So algebraic geometry seems very, very good and amenable to something that we're inching towards. So just to wrap up this first lecture, at the time when they were doing this, their motivation was this fact. Right? E8 has this subgroup. I mean, this is the standard model. At the time, at least 20 years ago, Witten was still saying that the heterotic string is still the best hope for the real world. I don't know whether it's changed its mind. I don't know. But I want, again, this is not a lecture on string phenomenology. The point is, at the time what they were doing, that the SU3 bundle, the tangent bundle of Calabi-Yau, the commutant of SU3 in E8 is E6. So at the time they got to E6 gut theories. Again, this is very much improved on today, but you know, this is 1980s when people were still thinking about E6 gut theories. You know, how can you write down the entire standard model spectrum within a single semi-simple Lie group? So E6 worked, and in fact, you can we all remember that the fundamental representation of E6 is 27-dimensional. So all of the fermions of the standard model can actually be packaged into a single 27 representation. That's why people did guts. And if you work out the cohomology, this corresponded exactly to H1 of the tangent bundle, and the 27 bar is the H1 of the cotangent bundle. And this, by Hodge decomposition, is exactly H21, and this, by Hodge decomposition, is exactly H11. Okay. Again, I want to emphasize this: we don't do this today. We're much more sophisticated in doing this. We now today, to find exact standard model, we do a more sophisticated bundle value cohomology, which is just fine. It's still a very similar technique, but this comes to be known as the standard embedding. It was the first serious effort for string theorists to try to reach the standard model. So this is a really concerted effort, right? Because you know, at the time they were writing down the string effective Lagrangians to unify, you know, to get into the graviton, into the Lagrangian, the mode expansion of the string. But all of a sudden they were thinking about something very specific. Is it possible to incorporate the exact standard model spectrum? So anyhow, at least we get the number of generations from this story. And the number of generations is 3, right? We know 3. We know this from CERN experiments. So, but 27 minus 27 bar is exactly a half of the Euler number. So when Strominger went to Yau to ask him to actually write down this problem, right? So Yau knew that there's only one case for d equal to 1, 2 cases for d equal to 2, and d equal to 3, he says, oh, it's impossible. There's so many, we don't have no idea. But at least he was able to give these 5 examples. Why wasn't Candelas, Strominger, Witten, and Horowitz happy? Because they wanted Calabi-Yau threefolds with Euler character plus minus 6 because of the 3 generations, 2 times plus minus 3. So which depends on, you know, which one you call the generation, anti-generation, depends on taste, right? So so immediately the quintic didn't have this property, right? Its Euler number is minus 200. And the physicists were looking for Euler number plus minus 6 manifolds. It is still true today, at least in the context of heterotic compactification, that people are not looking for, they're looking for you know, geometries with bundle index plus minus 6 or plus minus 3 or some version plus minus 3, which is, this is the sort of the baby version of what they do. But even this problem was already sufficiently complicated that Yau didn't immediately know the answer to, which is kind of interesting. But this prompted, in some sense, now we're getting to the heart of what I really want to talk about. is the era, I would say, the era of data science in algebraic geometry and in physics. Why? Because of this. You know, here's a problem that we know to be a proliferation of, right? There's an entirety, this space that's kind of unexplored even by the mathematicians. And you immediately try to write down some simple constructions, and they didn't satisfy the kind of physics you wanted. So of course, you know, this is something that, you know, young people would grow to appreciate in the course of their careers, is that if you go to a pure mathematician, you ask them for a specific answer, you'll never get it. Because mathematicians and pure mathematicians are never interested in explicit construction. Well, they do, but they won't tell you that. For them, the theory and the beautiful architecture is much more important. So, and in this case, you know, when Yau proved the Calabi conjecture, now that was is in fact a non-constructive proof, in the sense that he actually, till today, we still don't know a single compact Ricci flat Kähler metric in terms of analytic functions, because he just showed that the Monge-Ampere equation can be solved. And in fact, it's so complicated and no solutions ever been found. He just said that it can be solved and the solution exists and it's unique, right? So Yau was already very gracious in telling the physicists that there are these examples, which are called cyclic manifolds, by the way. But these ones had very peculiar Euler numbers that didn't make the physicists that happy. So what do you do? I mean, mathematicians didn't have databases at the time. I mean, this is mid-1980s. And it's also, you know, databases is not what pure mathematicians do until today. I mean, now actually a lot of pure mathematicians, a lot of whom I work with, do write down in large databases. And I will get to that shortly. And you know, this is what people, and now it's okay. It's no longer embarrassing for a pure mathematician to say, oh yeah, by the way, I have a hard drive of 5 million manifolds. It's totally cool. But this mindset is actually really recent. It's found in only the last 10 years or so that algebraic geometers, maybe 10, 20 years or so, the algebraic geometers would actually sit down and say, well, here, look, I have a hard drive filled with these things. Let's play. And that's part of the reason why we are where we are today, that we are capable of doing something like this, because of this compilation of these data sets. So that's something I'm going to get into. I think I'm out of time for this lecture. In the next lecture, which what I'm going to do is I'm going to give a very quick overview of some of the databases that have been constructed in the past 40 years, since 1986. And then I will give a introduction to machine learning 101, and sort of what can you do with this data, and then we're going to move on to how we're going to play with it. So I can pause here for questions. I think I'm exactly on time.
Yeah, thanks very much, Yang. You were precisely on time. This is 4:30. So let's see. Are there any questions? Yes, so there is a question in the chat box, so you might want to.
Yeah, good question. So I just want to read out the questions. Does a similar classification like Calabi-Yau exist for R greater than 1 or greater than 0 Calabi-Yau? Good. So something I wanted to emphasize is this trichotomy classification theorem for Kähler, and I think it's even true for general complex manifolds, is that this column of positive curvature is known as Fano varieties. So I will type out these words. So so Fano is greater than 0. So Calabi-Yau is equal to 0. And then these things are less than 0 is called general type. So there's a theorem, it is a known theorem, that Fano varieties, the topological type of Fano varieties in every dimension is finite. So there is a classification for them. I don't know how far the classification program has continued, but it's known to be finite. That's a theorem. Calabi-Yau, this middle column of Calabi-Yau, the finiteness of topological type is a conjecture of Yau, and it's still open. We have no idea how to even handle this. And this one, the general type, the negative ones, you see, it's already pretty bad, right? In dimension 1, you got you got one case, infinite family. That's dimension 1. In arbitrary dimension, the negative curvature Kähler varieties, or I think negative curvature complex varieties in general, are unclassifiable. I think they're actually unclassifiable. As in, it's if you try to do it, it's a Turing incomplete problem. But don't quote me on that. I believe it's certainly not classified, and we know there are infinite families of these, but it's very, very untamable. That's why it's called general type. In fact, the generic manifold, the generic algebraic variety you write down in some kind of complex projective space embedding, it's going to be general type. So that's kind of sad. But if you hit on the final case and Calabi-Yau case, you luck out. This is why there's been so much work on mirror symmetry for Calabi-Yau manifolds and Fano varieties, because these are the ones that you can actually get a handle on. I think for general type, it's almost hopeless. At least that's the word that I hear for algebraic geometrists. They don't try to do anything with those because there's too, of course, from a data science point of view, it doesn't matter, right? I mean, this is even better. We got infinite amount of data for this, and it'll be very nice to plot. The closest that I know to sort of a vision of general type is it's in append, as everything is, it's an appendix of Hartshorne, and I think Hartshorne tried to plot complex surfaces, dimension 4 objects, and he was trying to do a plot of like let me see if I can find it. So I'm going to try to walk over to find my yes, it's my Hartshorne. A plot of this, and I think that's what that's a very good question, by the way. I remember there was Hartshorne is a very, very special book in the sense that anything useful in it is in an appendix somewhere, and it's not actually in the it's actually not in the actual main text. So there we go. So here is a there's things that look like this, right? So this is
Sorry, Yang, you got muted for some reason. Sorry.
Okay, sorry. Did you get the bit about Hartshorne?
No, can you please repeat that? Yeah.
Oh gosh. So what point did I mute myself? Sorry.
Just before you were showing the page.
Okay, so sorry. So I was just saying that anything in Hartshorne, useful stuff is probably in an appendix somewhere or an example somewhere there. So he was trying to plot like in CP3. If you try to do curves in CP3, what's likely going to be like degree versus the existence of curves. So this is kind of early versions of classification results. So this is his chapter 4 on curves. So it's kind of interesting that, as far as I know, this is one of the only ones from the early days of algebraic geometry that people were thinking about this sort of thing. Yeah.
Okay. Are there any other questions? Let's wait for a couple of minutes. I mean, there might be a
sure
questions. So maybe Yang, I can ask you a naive question in the meantime.
Of course.
So is there, if we fix the Euler number to be plus or minus 6, is there any conjecture as to how many Calabi-Yaus are there?
That's a very good question. So you want to take a slice of that? It's certainly going to be finite.
Do you think if we plotted the number of Calabi-Yaus as a function of Euler number, there would be some peak near plus or minus 6?
Sadly not. Sadly, I mean, you're anticipating several plots that I will show you. Within certain classes of manifolds, with certain classes of constructions, you can plot it, and the peaks are pretty random.
Okay.
Yeah, I mean, there's no mathematical reason for selecting plus minus 6.
Okay.
Yeah, but that's very good. I mean, it would be great, right? In some sense.
Yeah, exactly. Yeah.
In fact, within the database of all known Calabi-Yau manifolds, if you lump them all together, the most typical Euler number is actually 0.
I see.
It's they're the self-mirror ones.
I see.
But quite a bit. There are millions of them, as opposed to there are hundreds and thousands, but there are millions upon millions of self-mirror ones.
Okay.
For some reason, I will show you exactly these plots.
Great. Yeah. Okay.
Yeah.
Okay. Yes. There is another question. Yes.
I believe so. I'm not an expert in this, the general type classification problem, but I think it is ultimately related to sort of amenable topologies not being classifiable for those cases. I think that's why they've been called this very boring name, general type, because they're too general. In fact, I should quote the theorem. At least a specific corollary of the theorem. I think this is what Mark Gross told me. Every Calabi-Yau threefold can be realized into CP3. That's a very CP7. This is a very general result. I'm going to type out every Calabi-Yau threefold is in CP7. So in other words, if you take 8 projective coordinates.
Yang, you are actually doing a direct message to me, so not everybody is being able to see.
Oh, sorry.
So you have to change it to everyone.
To everyone. So this is Mark Gross. He told me this fact. I think. So that's a very powerful. In fact, every Kähler is in CP7. A Kähler threefold is in CP7. So this entire so there are trillions. Now we know at least 2 billion Calabi-Yau threefolds, and all of them can be written in just 8 projective coordinates. It's just because your polynomials can get very, very complicated, right? So you could be 500 not complete intersection polynomials in 8 variables, but you can always do it. 8 variables is enough. And there's a general theorem. I forget what the counting is, but every Kähler n-fold can be written in CP something like n plus something divided by, there's some kind of an embedding theorem, which is a bit crazy, right? In the sense that the entirety of any problem you ever want to consider in algebraic geometry or in differential geometry or in geometry of manifolds can be realized in a very small number of variables. And that's exactly the thing I want to emphasize, because it's not that bad, right? I mean, in terms of, if you look at it from a data science point of view, it's not that bad. It's just 8 variables. Oh, for Calabi-Yau for Kähler threefolds. But the number of possible addition, the number of polynomials can grow to infinity, even though you have just this number of variables.
Right. Okay, so I don't see any more questions. Yeah, there is one. Yeah, so Loga is asking.
Very good question. There's a program led by Philip Candelas and friends. I think and Andrei Constantin and friends. I think Challenger Mishra was involved in this. They're looking for. They had been looking for in the last 10 years or so small Euler number Calabi-Yaus, for example, just by brute force. That's a very good question. There have been machine learning searches for small index bundles. And you see where I'm getting with this, because those are ones that are likely to give standard model. So I've been involved a bit with that. Just trying to see, to train some kind of neural network that picks out the ones that are likely to give standard model. But specifically this question of constructing Calabi-Yau's small Euler numbers, I don't think that has been done. It would certainly be interesting to do it. I mean, just to see. Of course, from a physics point of view, small Euler number Calabi-Yau threefolds is, as I said, it's not that interesting anymore, because we're more sophisticated. We don't just do E6 gut theories and sort of in standard embedding. We've gone a bit more, but we are looking for small index bundles on Calabi-Yaus. At least within the heterotic community, people have been doing that. But if you want to just ask a pure mathematical problem, how do you construct small Euler number Calabi-Yau threefolds? That certainly would be a very interesting problem to set up, to see whether small Euler number is very different. Yeah, that's a good question.
Yeah, so Bhavay is saying that you typed another statement before this. Could you send that to everyone as well? So I think it got directly messaged to me.
You typed another statement.
Yeah, so that was Fano greater than 0, Calabi-Yau equal to
0. Sorry. Yeah, sorry. This one here and that.
Okay, so I don't see any further questions. So let's thank Yang for a very nice lecture, which sets up the next two lectures very nicely. So we will reconvene for the second lecture for today at 7:30 p.m. IST. The second lecture is going to be by Tom Hartman. Okay, so thanks again.
Thank you very much, and I'll see you Wednesday at the same time.
That's right. See you on Wednesday. That's right.
Great. Yes. Thank you very much.